Lines of best fit, scatter plots. If we can determine that a linear model works for a set of data, so we got a bunch of dots on a scatter plot and it's not a quadratic or a U-shaped, it's not an exponential, it's not like no correlation all scattered all over the place. If it's, we can tell it's kind of going up linearly. We can see if there's a correlation between the sets of data and or how strong that relationship is between the two sets of data. A correlation coefficient is a measure of how strongly related the data is. We use the letter R to talk about how strong or weak data is, and a number will be given to tell us how strong it is, and it will always be between 0 and 1. Sometimes it's positive, sometimes it's negative, but it'll always be between 0, 1 or 0, negative 1. The stronger the data is, the closer R is equal to 1. And then the weaker the data is, the closer it is to 0. And of course, if it's 0, then there is no correlation. If it's at 1, we'll talk about it in a second. So we got some scatter plots right here. We can tell those, we could draw a line through those. Those would be linear. And over on the far right, we got perfect positive and perfect negative. Those are, pretty much straight lines. And over on the far left are strong positive and strong negative. It's not perfect, but it's really close together. Those dots are really close together. Weak positive and weak negative, you can tell that, weak positive's going up the hill, but they're a little bit more scattered out than the strong one. Same kind of stuff here. The weak positive and weak negative, those we're going to represent those as 0.4 and negative 0.4. Notice if it's positive, it's positive 0.4, and if it's negative 0.4. And it's really any number that's kind of close to 0.4. These aren't the only 6 numbers, or only 3 numbers with negatives that there are. It could be any sort of decimal, but these are the ones that show up that they're really, really close to. So 0.4, if it was 0.43, 0.44, or 0.36, those are really close to 0.4. Those would be considered weak positive or weak negative if there's a negative sign out front. Strong positive, any kind of number that's really close to 0.7, so like 0.75. Or strong negative would be negative 0.65. That's really close to negative 0.7. Perfect, those would be ones. And honestly, if it's like 0.98 or 0.99, we're probably going to consider that perfect, even though the technical definition is 1. When the data can be shown in a linear model, like we've talked about, math people oftentimes like to create what is called a line of best fit or a regression line. So a line of best fit. If you look down at this data right here, it says the mean test scores and the study time. Well, that line that we drew in between those, it doesn't exactly hit all of them. It doesn't go straight through all of them, but it gets really close. It's a good representation of what's going on there, and it's going to help us predict future outcomes. Okay, that is a big ordeal for us. So right here it says a teacher wants to look at the relationship between absences and grades. We know what that is. In general, the less you're at school or the more absences you got, the lower your grade's going to be. It just is what it is. If you don't show up to school, you don't make good grades. You show up to school, odds are you're going to have a better grade. So this says estimate a line of best fit for the data in the table. I don't even want to estimate it. I want to find an exact line of best fit. And we're going to do that here in a second. So what I would encourage you to do is to draw all of these, plot each of these points right here. So like you'd have 0.89 right there. I'm trying to do this on my laptop, so yours will be better than mine. 186 would be like right there. 284 right there. 381, 478, 573, and 664 would be down there. 771 would be up there. 865 would be right there. And 966 would be right there. And obviously, if we wanted to draw some sort of line of best fits, something like that. It doesn't have to be perfect, but if you were eyeballing it, I'd probably shift it down a little bit just because my computer or whatever. But, something like that would be a good estimate for my line of best fit. And you can find your y-intercept is probably around 90, 88, somewhere around there, 87. And your slope's going down the hill. It's going to be negative. You could do your rise over run, count all that. I don't want to do any of that. I want to get an exact answer. Forget estimating. Let's get an exact answer here. So how do I get an exact answer? I come over here to Desmos. I'm going to type x1 equals brackets. So I'm going to type all my x values. In this case, that would be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I'm the moron that didn't put them inside the brackets. So let's fix that real quick. Make sure yours are inside the brackets. There we go. I got 10 elements on my list, and there are 10, 1 through 9, and then 0 up top. Y1 equals 89. 86, 84, 81, 78, 73, 64, 71, 65, and 66. I got 10 again. Very, very important that if 0 is the first number in your list over there on the left side for X1, then 89 needs to be your first number for Y1. Those have got to match up. If this is the, eighth number, if 7 is the eighth number you're in, then 71 needs to be the eighth number. Make sure that you go in order each time, or it's going to be completely wrong. So, with that being said, I'm going to come over here, and a line of best fit, a linear model would have y equals mx plus b. So I need to find m and b. I need to find my slope and my y-intercept. Okay? And so, I got to speak Desmos here. Desmos doesn't understand y equals mx plus b. Wouldn't it be nice if I just punched that in and it gave it to me? It doesn't speak that. We got to speak Desmos. Y1, and then squiggly, I'm going to hold the shift, and then on top left, Y1, squiggly, equal, or it's not equals, squiggly, mx1 plus b. So that's speaking Desmos for y equals mx plus b. So punch in y1 squiggly mx1 plus b, and it's going to give you a lot of good stuff over there. R, that's your correlation coefficient that we just talked about. The closer it is to 1 or -1, the stronger it is. So my R right there on the left side, right there, says negative 0.94. That would be really strong negative. Really strong negative, okay? Down here, it says my slope. It gives me my answers down here. My slope is negative 2.8, and you could call it negative 2.9, negative 2.87. I'm just going to write negative 2.8. And my y-intercept was 88.6, and you could write 88.7 if you just think you're snooty rounder person. So, all right, so I'm going to have y equals negative 2.8x plus 88.6. And that's my answer. That is my line of best fit right there. Okay? And we could estimate different points because of that. We could say, okay, what do you expect someone with 20 absences to have on the test or in the class? So if that was the case, I'd take 20 absences and I would just plug that in right there. And that would help me estimate, hey, based on this line of best fit, this is what the kid's probably going to have. Now, they could be some sort of outlier somewhere, but it would give us an estimate as to what they would be. Bill is the guy who checks your receipt at Costco. He's made a note of the number of ice cream and air conditioner sales over a 13-day period. We want to find the line of best fit. And we got to answer the question down below. Now, why does this problem stink? This problem stinks because, look at the last one, it gave me all the numbers. This one stinks because I ain't got any numbers. I got to find all of them. And I got to make sure I've got 13 of them when I'm done. So what I do is I usually make a T-chart just like this. And then I start down here on the bottom left. And I would say that's 10, 2. And then I would say 26. That's that one. And then I got 2010. That's that one. And then I got, what, 34. And I got to make sure I write a little better here. I'm copying them down here a second. And then I've got, what's after 34? 48. And then I've got 58. And then I've got 50, 12. I'm going to make me another T-chart over here so that I can... Oh, why did I put it 12 there? How about a Y right there? All right, so 50, 12 is the last one. And then I've got 60, 14. 60, 14. 70, 10. 70, 12. 80, 16. And 80, 18. And lastly, 90, 16. All right, let's make sure we got 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of them. Sweet. There's my chart. I'm going to come over here and I'm going to type in x1 equals brackets. And inside those brackets, I'm going to type all my x values in order. 10, 20, 20. I put a period instead of a comma like a moron. 20. Did it twice. Look at that. 30, 40, 50, 50, 60, 70, 70, 80, 80, 90. 13 of them. Next are the Y's. Make sure that you go in order. 2, 6, 10, 4, 8, 8, 12, 14, 10, 12, 16, 18, 16. 13 of them again. Now I got to speak Desmos. Instead of y equals mx plus b, Desmos likes y1, squiggly, mx1 plus b. Gives me all my important stuff. R equals 0.86. That would be strong positive. M is 0.16 and B is 2.19. So I'm going to say Y equals 0.16. It might even say like 0.2 if you got it on a test or something. X plus 2 point. I'm going to write 2.2. Okay. So based on the line of best fit, what would be a good prediction for the number of air conditioners sold if 55 ice creams were sold? Well, ice cream sold, those are all my X values down there. So I want to plug in 55 for X right here. I would plug in 55 right there. I'd have Y equals 0.16 times 55 plus the 2.2. Sorry, I'm punching it in all over there. Now I got to punch in my calculator. 0.16 times 55 plus 2.2. I got 11. So 11 would be what we would expect if there were 55 ice creams sold. Okay, let's look at another one. The age and height of the first 11 guests on a Disney World ride were recorded in the table below. Tower of Terror, top-notch ride. All right, it wants us to make a scatter plot here. All right, so 646 would be right in there. And then 1156 would be right in there. 1964, heck of a year, is right there. 542 would be right in there. 852 would be right in there. 1256 is right there. 1463, I'm sure, was a heck of a year too. 751 is right there. 1360 is right there. 1763 sounds like a great year too. 954 right in there. Okay, we could draw a line through that and just kind of estimate a line of best fits, or we could go to Desmos and type it all in. So Prefer just to get it all right. Let Desmos do the work for you. So I'm going to type in all my x's. 6, comma, 11, comma, 19, 5, 8, 12, 14, 7, 13, 17, and 9. There are 11. It said there were 11 guests at Disney World. So far, so good. Y values, I got 46, 56, 64, 42, 52, 56, 63, 51, 60, 63, and 54. 11 again. Let's speak Desmos. Y1, squiggly, MX1 plus B. Woo. M is 1 point, let's call it 1.5. 1.49, and then this would be 38.7. So my line of best fit would be y equals 1.5x plus 38.7. That is my line of best fit. If we wanted to estimate what someone's, height would be if they were 30 years old, or if they were 10 years old, then we could punch that in right there for x. So let's look at the next slide, talking about that one. What is the correlation coefficient? We just talked about that. R is over there, and that is 0.94. That would be strong positive. Which of the following statements best describes data as age increases, height increases? A would be your correct answer. Based on a line of best fit, what would be a good prediction for the height of someone who is 34 years old? So what we would do is we would type this in, y equals 1.5 times 34 plus 38.7. So I'm going to type that into my calculator real quick and say 1.5 times 34 plus 38.7, and that gives me 89.7. So I think that we're dealing with inches tall here. So 89.7 inches tall. And we got our answer. We're feeling great about it until we read that next question that says, why is this one weird? Well, I got the right answer. I did everything my teacher said to do. I don't know why it's weird. Well, 89.7 inches is equal to about 7.5 feet tall. So, why is this one weird? It said that based on this line of best fit that we've got, if you kept going over here to 34 years old, that someone's going to be like up here really, really tall. If I were punching, a grandma that's like 95 years old, she's going to be like dunking the basketball, backflipping. Like, that doesn't make any sense. Why am I saying all this? I'm saying all this because these lines of best fit sometimes only work for a given set of data. So like we have this area maybe between, 4 years old right here and maybe between 20. Like you could make a straight line, and we did. It was strongly correlated. We did all the right things. But that, you only get so tall. Like this would just kind of flatten out and plateau. So it's not going to work for anybody maybe after 18, 20 years old because you just don't keep getting taller after that.